All right, let's talk a little bit about combining like terms. So, if I have one banana and I add another banana, I have two bananas. Our combining of like terms is going to be the same idea. Students often make a mistake where they add terms that have different powers, and we don't want to do that because when they have different powers, they're scaling differently. But if I were to have something like 2x, my pencil turned off. If I had something like 2x plus 3x, I need to be able to say it in English for it to make sense. The second I have to think about what the power is going to be, I probably am thinking about it too hard or I did it wrong. So I have 2x's plus 3 more x's is equal to 5x's. I need to be able to say it in English like that. Now, if you really want to expand it out, multiplication means you have two of these things that it's multiplying against being added together. So I could expand this out in the same way I did in my exponent property video and say that this 2x is x plus x. And this 3x is x plus x plus x. Bring down my addition sign. And notice I have 5 x's being added together, which is the definition of multiplication. 5x. So it works the exact same way. It's just one step down in abstraction when we're talking about powers versus multiplication. That's all it really is. 2x just means x plus x. 3x just means x plus x plus x. A lot of times students forget that, and they make weird magic happen. But one thing that doesn't work, if I have 2x plus 2y, number one, I can't say it in English. I have 2 x's plus 2 y's. What does that equal? A lot of times students will do like 2xy or 4xy or something like that, but it's not that. This cannot be simplified because there's no like terms. I can't say it in English. The second I say this, the number sentence or whatever you want to call it, the algebraic sentence out, it doesn't make sense. 2x's plus 2y's. I wouldn't say, 2 bananas plus 5 apples is equal to 7 apple bananas. That wouldn't make sense. It just ends up becoming nonsense. The same goes for 2x plus 3x squared. A lot of times students will try to say that this is like 5x cubed, but what made the power change in that idea? Sometimes students say that, and I'm like, well, what changed the power? Remember, multiplying by the same thing changes the power. That's the only thing that changes the power, or dividing by the same thing. Those are the only things that change the power. So in this case, remember, this is an invisible 1 right here you can always write when you just have x. Notice they have different powers. So I have 2 x's plus 3x squared. Again, can't say it in English. But let's go ahead and just expand it out. Remember, 2 times x is equal to 2 of those things being added together. Bring down my plus sign. And then that means I have x squared plus x squared plus x squared. Notice I only have 2 x's being added together, and then I have a bunch of x squareds being added together. And when you completely expand it, you notice these don't even look the same. They're separated by different operations. So if I were to use just numbers in here, if x was like 3, we'd have 3 plus 3 plus 3 times 3 is 9, plus 3 times 3 is 9, plus 3 times 3 is 9. So if you actually put numbers in here, it wouldn't make sense. But I'm going to say does not equal. So this can't be simplified. But I'm going to do what y'all do. I'm going to say does not equal what did y'all do? Y'all usually do 2 plus 3 is 5, and then you say x cubed or something like that. Does not equal this. Now, let me go ahead and say x equals 3 and plug it in and see what happens. On the left side, I get 2 times 3 plus 3 times 3 squared, which is 6 plus 3 times 9. 3 squared is 9. 3 times 9 is 27. So I end up getting 33. But over here on the right, I get 5, which, by the way, since there's a multiple of 5 here, you know it can't be that because this doesn't end in a 5 or a 0. I get 5 times 3 cubed, which is 5 times 27, which is, what is that, 135? 5 times 7 is 35, plus 100, 135. So notice these aren't the same number. And if I made an arithmetic mistake or something like that, then go ahead and check it. You'll still see it doesn't it doesn't end up being the same thing. And the main idea here is that if you were to plug in like a number like 3, I don't really like to choose 0 or 1 because sometimes those can end up being niche cases where it may look like it works. But if you want to plug in a number like 3 or something like that, whenever you simplify, and make sure that what you get before and after simplifying should be the same. Simplification should never change your answer. It should never change the function of the actual expressions. So this can't be simplified. But let's look at some that can. So let's say I have 2x plus 3xy plus 2x squared plus 2xy, or let's change this to yx. I know you're probably that I kind of spoiled it, but it's fine. So let me look at this. What my process normally is for combining like terms is, number one, they need to be added or subtracted. Different terms need to be added or subtracted. When we multiply, we're going to mess with exponents and things like that. We need to watch out for that. Combining like terms only really works with adding or subtracting. So you need to kind of put that in your brain somewhere and remember that. I don't make that mistake anymore. I did when I was a kid. But I could totally see how you could make that mistake. Sometimes students, and usually it comes down to students being confused about what the operations actually mean. That's what I want to kind of avoid. I want to kind of make you understand why these things work. So when I look at this, I look at these and I say, all right, I'm just going to look at the things that are in common. So I have 2 x's, and I don't see any other terms that are just x. It needs to be just x or a number times x. But it does not need to have any other variable factors. So if I look at this, I have 2 x's plus no other x's, so I just have 2 x's. And then right here I have 3 xy's. I can't combine it with this. No. Can't combine it with this. No. But this may not look like it, but you can combine it like that. Remember, you have to have the same number of factors and type of factors. So notice this has a factor of x and a factor of y. This also has a factor of x and a factor of y. Same powers, just a different order. But multiplication is commutative, so you can change the order. If you want to convince yourself more that y times x can also be written as x times y. So now, if you want to change the order of it like that, just to make sure, you look at 3xy's plus 2xy's is 5xy's. And then I have a 2x squareds. I have 2x squareds plus what? I don't have any other x squareds, so that's it. And then same thing with 3y squareds. You don't have any other ones. And again, students often, let's say I have 2x squared plus 3x cubed plus 2x squared plus 5x cubed. So I look at this and I like to go to my highest power first. It doesn't really matter what order you're doing it in. So I like to go with my highest power because we usually write, like right here, I didn't write this like I would normally write it. I usually go to the highest power first. So that's my leading term because that's the most important part to understand the behavior of your expression or your function. So I have 3x cubed plus 5 more x cubes. I get 8x cubed. And then I have 2x squared plus 2x squared is plus 4x squared. Notice how I did not change my power when I was adding or subtracting. There is nothing that will change your power on any of your factors when you're adding or subtracting unless it cancels the entire term. But that's how all of your combining like terms are going to be. You just need to make sure that you look at the number as how many of the thing it's multiplying against, how many of those that you have. And then what you have right here, you need to make sure if you combine it with anything, they need to have the same exact factors. Even things like this, 2a squared b plus 3ab squared. These are not the same. Notice if I were to expand them out, you can see it more clearly. A squared is a times a, and then you just have that b there. Notice how when you expand them out, it's easier to see that they are not the same. You've got to remember that the exponent only affects the thing directly to the left of it. A lot of times students will write a plus b squared and pretend that the whole thing's squared, but in this case, only that is squared. Though if you want to have them both squared, it would have to look like that. In a future video, I'm going to talk about distribution, and I know I talked about it in the last one as well, but I don't want to confuse you because we're not talking about it this week yet, because we're about over with this week. But I'm going to take that, I'm going to show you how to distribute that. It's going to be very similar to this idea, where you distributed this onto both of those. But I'm going to have a whole video on distribution.